Okay, so I wanted to. Okay. I wanted to talk just, briefly about some more stuff about rotations and look at angular momentum very briefly. We're about out of time, so. All right, so rolling bodies. Okay. So here's the ground and here's an object. Okay, it's not hovering. It's actually touching the ground. Somebody needs to mute. I can hear you doing something. Okay, so let's say the object's rolling along. It's rolling without slipping. Then this is, I'll call it, V center of mass. That would be like a wheel is rolling by you and you're looking at the center of the wheel and you're measuring how fast that center is passing by. Okay? But it's rolling and these areas on the wheel, the other parts of the wheel, are not traveling at V center of mass because of the rolling. Okay, if it were sliding, all the particles would be traveling at this velocity. Okay? So let's look at a point here and a point here. All right? So that's the point of contact and then a point at the top of the wheel. The point of contact is traveling at, if you take a snapshot of this thing rolling along. The velocity at this point, V, is equal to 0. Okay? It is stationary. The point at the top, because of V center of mass and because of R omega, this is going 2 times the center of mass. Okay? V center of mass. This is the one, this one's easy to think about. I mean, for me, maybe for you it's easy, all of it's easy, but for me, this one's easy to think about because I think about this thing going by and this is going really fast and so forth. But this one always tripped me up. But the way I think about it is, if this point were not traveling at V equals 0, so if it were not stationary, it'd be sliding, and it's not. Okay? So anywhere along the motion, when you look at this point, it's actually traveling at 0. All right. So let's get a relationship between this V center of mass and the rolling of the object. So think about this object as it rolls, okay? It travels some distance, call it delta. I'll just call it delta S, okay? So it travels some little distance, delta S. Well, that's the center of mass traveling that distance, delta S, okay? And that delta S is equal to V center of mass delta T, okay? And that's straightforward. That's just how far it traveled, and you have the velocity times the time. All right. But we know that delta S is equal to R delta theta. We talked about that the other day. If you have this radius times some angular displacement, then the arc length is delta S. All right? So we can equate these two. R delta theta is equal to what? V center of mass delta T. Okay. Move this around and you get R delta theta divided by delta T. Let me not write it like that. You get delta theta divided by delta T is R. Shoot. I got it in the notes and I'm just, okay, here we go. V center of mass divided by R. Okay. V center of mass divided by R is equal to this, which is omega. So, in the end, V center of mass is equal to omega R. All that work to get that result. But this is nice because if you know the angular velocity and the radius, you can easily calculate the velocity of the object as it's rolling. Okay? So these rolling objects, not only do you have the kinetic energy of this translational motion, you have the kinetic energy of the rotation, and so the kinetic energy of rolling KE, this is for rolling, you get KE of rotation plus KE of translation, and that is equal to 1/2 I omega squared plus 1/2, I'll write it as big M since we've been using big M for the mass of these rotational these objects under rotation. 1/2 mv squared. So the kinetic energy is due to the rotation plus the translation. I'm not going to derive that. I mean, I hope it makes sense. You're rolling and you're going along. Well, it is rolling. It's rolling along and translating. Let's look at an example. Maybe this will, based on this idea that V center of mass is omega R and the total kinetic energy is rotation plus translation. Let's look at an object rolling down a hill without slipping. Let's see. I'll put it right here at the bottom. Okay. So it's right on the edge, and this distance is h. Okay. So let's make this a disk, and it starts out up here at MGH. It has radius R. Now you might say, well, look at this. The center of mass is R above H. Well, okay, that's true, but the ground here, it's also R above H from where I defined the horizontal. So when this rolls down the incline, just from energy considerations, I'm starting out with mgh. All of that is going to be converted into kinetic energy. So it's going to be the kinetic energy of translation plus rotation. So it's 1/2 mv center of mass squared plus 1/2 I omega squared. Okay. So I'm going to calculate this final velocity when it reaches this point. So for the disk, the moment of inertia for a disk is mr squared over 2. Okay, so I'll use that for the moment here. And so mgh is equal to 1/2 mr squared over 2 omega squared. I know this is, I'm going to erase this. That's I plus 1/2 mv center mass squared. Okay. But we know, I always do that. But we know that, get rid of this. We know that V, from what I just did 2 seconds ago, V center of mass is omega r. So V center of mass squared is omega squared r squared. Okay. So omega squared, I want to write it as omega squared. Because I'm going to replace omega, since I'm looking for that final velocity, that final translational velocity, I'm going to replace this omega squared is equal to V center of mass squared over r squared. Okay. So, mgh is equal to 1/4. You have a 1/2 and a 1/2, and you get an mr squared times V center of mass squared over r squared. So this becomes mv center of mass squared plus 1/2 V center of mass squared. Well, here's something interesting. Let's see what we can cancel. It's independent of the mass. That's no surprise, right? And you get V center of mass is equal to 4GH over 3, all underneath the radical. Is there anything surprising about that result? I don't know, maybe not. It's independent of the radius. Every disk would have the same final velocity. Okay? Every disk, independent of mass and radius. So a disk this big and a nickel will have the same final velocity without slipping. All right. If we had more time and if I was able to do some demos for you, I would show you how different objects will reach the bottom of an incline at different times, independent of their radius and their mass. Like every disk will beat every spherical shell. it depends on that moment of inertia. It depends on how the mass is distributed on the object. Okay? So you can take, I've got, back at CVU, I've got some, big discs and little discs, and they'll roll exactly the same, and then you have big spheres, little spheres, disc versus sphere, hoop versus disc. Okay, so I do all these little races, but oh well. Maybe when we get back I can show you. Okay. So that's the idea. I mean, you start out with this potential energy. It's converted into the kinetic energy of rolling, which is rotational plus translational. And you can equate the variables using V center of mass is equal to omega R. Let's look at an acceleration example. Very similar to this, only I'm going to use force this time. Okay. Here's an object that's going to roll down a hill, just like in this case I'm going to use force and calculate accelerations. It's going to roll down a hill, or I say a hill, an inclined plane without slipping. What forces are acting on the object? Okay, well, you have mgh, the normal force that is not in that direction. The normal force is in this direction. Okay. And there's a static friction force. The static friction force is right here. Okay. Anything else acting on this? Got mgh, the normal force, and static friction. I think that's it. So, since this is rolling, we need to pay attention to, well, it's translational motion and rolling motion. So we need to pay attention to the forces acting, the translational forces, and the torque. So about the center, because it's going to be rolling, it's about this center. There's a torque here due to the static friction force. Are there any other torques? No. This force is not providing any torque. This force is not providing any torque. So there's one torque due to static friction. So for the translational part, the sum of the forces, which is mgh sine theta. Okay, I didn't say it, but this is some angle theta. Okay. mgh sine theta, that's down, I'm going to make down positive. Okay. mgh sine theta minus the static friction force is equal to ma, center of mass. That's the translational part. For the rotational part, you have minus a, center of mass. The reason I put the negative in here is because this is a clockwise torque and it's negative. It takes a minute to figure out the signs to make these things come out correctly, but anyway, okay. Minus a center of mass is R alpha. We did that the other day. I showed that if you want to know this, well, this also comes from what I did previously. This is the way it works out for the relationship between the rotational acceleration and the center of mass acceleration. Okay, that's easy to show. So the second law for rotations, this is second law, rotations. We'll need this in a minute. Is minus R Fs, that's the torque, and that equals I alpha. That's the moment of inertia of this object about its center of mass. Okay. So, excuse me, combining these two, that's an Fs, I'm going to get rid of that static friction force. You get mg sine theta minus I, A center of mass, divided by R squared is equal to m A center of mass. Okay. Divide through, you'll see what I'm going to do here. Divide through by divide through by M, and you get G sine theta is equal to A center of mass plus I A center of mass over mr squared. So the acceleration from collecting variables, A center of mass is equal to G sine theta divided by 1 plus I over mr squared. That's a nice result because this is the moment of inertia of the object in general, be it a sphere, a hollow shell, a disc, a ring, a hoop, whatever it is, okay? So for the acceleration along an inclined plane, that's it. G sine theta over 1 plus I over mr squared. So the larger the center, the larger the moment of inertia, the smaller the acceleration. And you've seen this in action. I mean, you take something, it's independent of the mass, it's independent of the radius, but if you have something that has the mass far away from that axis of rotation, much harder to get it spinning than something that has the mass very close to the center, the axis of rotation. You think, well, this may not be independent. Well, there is a mass term in here, but that's going to be canceled by that mass that's in the moment of inertia. So we're running through this pretty quickly, but oh well. So let's talk about work, or I'll talk about work for rotations. Here is the idea, okay. This is theta. I don't know if I guess I called it delta theta. Doesn't matter. Delta theta, here's some radius r, and let's say there is a force acting on the object like this. Okay. So this object has mass, it's a circular object. You're applying a torque. We know that for a constant force, when I say a constant force, I mean a constant magnitude force. All right. The work is equal to F. In this case, this little length is delta S. Okay. So that's F delta S, and that is equal to F R delta theta, because delta S is R delta theta, and this is equal to simply the torque times delta theta. That would be for a constant torque, a constant force. It's the analogous thing to that linear work, that translational work. A force through a distance, the work in rotations is a torque through an angle. 1D motion. So the work, if I rewrite this is torque times theta final minus theta initial. Okay. That's for a constant force or constant torque. For the calculus version, the work is equal to the integral of the torque times d theta. Okay. All right. So if you want to know, how much work is being done on an object, torques produce angular accelerations. So if you want to know how much work is being done by a torque through an angle, that gives you the work in joules. So there is a relationship, just like we had in linear motion. There's a relationship between torque and angular. This is angular momentum. We haven't defined angular momentum, but you can imagine what it might be. Angular momentum, I'll write it in a fancy way right now. Angular momentum, we usually give it the letter L. L is equal to R cross P. Let me explain what that means. Okay. So here's an phooey. Here's an axis. Here's that position vector R. Here is the momentum P. Okay, this object here's a little massive object. It's rotating around some axis. Okay, then the angular momentum is R cross P. That is equal to, since P is mv, that's equal to m R cross V. Okay, and we don't have time to go into all the particulars of the cross product and all the fancy things we can do, but we will in physics 2 if we're back. I think we will be. I don't want to be a pessimist. Okay. So, just like we had in translational motion or linear motion, linear type forces, the net torque, I'm going to simplify this even more. The net torque on an object, okay, is dl dt. Remember, this is second law in angular momentum form. Remember second law with linear momentum, we had dp dt was equal to the net force. All right. So that's for a single particle. For a, I'll go ahead and erase this. This is for a single particle, point particle. For a continuous object, for continuous objects, we usually give those a capital L. Capital L is equal to I omega. It's simply that moment of inertia times its angular velocity. It is a vector. We don't have time to go into all the vector stuff about angular momentum. But it is a vector, and believe it or not, nature conserves angular momentum. Angular momentum is always conserved, just like linear momentum. Okay? And the net torque is equal to dl. Okay, is equal to dl dt. So you can do all kinds of nice, interesting problems based on this conservation of angular momentum, I omega. By the way, angular momentum has what units? Well, this has units of kilogram meters squared, right? That's the units for moment of inertia. This has units of per second. Okay. That's yeah, radians per second, but that's just per second. So lots of ways to write this. Typically, I'll see it written because a kilogram meter squared per second squared, that's a joule, right? You'll see angular momentum written in joule seconds. A joule second. There's no named unit for angular momentum that I know of. Just like linear momentum, there's no named unit. Okay? So joule seconds, kilogram meter squared per second. Now, okay, what I want to get to is this conservation of angular momentum. So it's a conserved quantity. So that means L initial, and it is a vector, is equal to L final. You take any isolated system, okay, and you somehow interact angular momenta, and the total angular momentum of that system will always be conserved. The classic example is an ice skater. All right, remember that L is equal to just in not just magnitude. L is equal to I omega. So angular momentum can change if the moment of inertia changes or the angular velocity changes. So you've all seen an ice skater do their twirl. How do they get going so fast? Okay? their initial angular momentum, we only got a few minutes, but I'm going to go ahead and I'm going to post some more examples, and of course I'll assign a few problems, and I'll post on YouTube all the problem explanations. And if you guys want to get together whenever in the next week or so, that's fine with me. So I'm at home. Okay. Here's the ice skater. Initial. L initial. I'm just going to say I small omega. No. This is initial. Okay. I large omega small. Okay. So they have their hands out and they're spinning. They're going really slowly and they're spinning, and then they bring their hands in and they start spinning faster, because they are changing their moment of inertia. They're changing the distribution. They're not changing their mass, okay? They're changing the distribution of the mass. So their mass is very far out from that axis of rotation. When they bring their hands in like this, then the mass is coming into the center, that axis of rotation. So L final is I small omega large. If I decreases, omega must increase to conserve angular momentum. They're an isolated system. Forget about that little bit of friction that they have on between the ice and the ice skates. Okay, and we have a real nice demo. You've probably seen it. I'm sure there's plenty of places on YouTube you can watch it. The rotating stool, you take masses and you start a person rotating, and then they bring them in and they start going fast and so forth. Okay. Another neat thing about this is angular momentum conservation is really cool. Spinning tops, gyroscopes, man, we could talk about those for weeks, but if you spin up a gyroscope, because of that conservation of angular momentum, it wants to stay in its original position. And this is how satellites and spacecraft get guidance. They spin up the gyroscopes and they're in this thing called a gimbal. So there's no net torque acting on the system. And that gyroscope stays spinning exactly like it started. And they do guidance around the gyroscopes. Okay. All kinds of cool stuff. Prop planes. Prop planes. If you have one prop spinning this way, you have the other one spinning this way. You get zero angular momentum. You don't want a net angular momentum as you're flying. It makes it weird, like turning a bicycle wheel. You feel that resistance, okay? Anyway, all kinds of cool stuff with angular momentum. All right, that's all I got.